Hey everyone, today we're going to be looking at the classification of matter or matter classification. Don't forget that you have a graphic organizer which follows along with these slides fairly nicely. So let's go ahead and get started. First off, well, what the heck is matter? Not what the heck is a matter, what the heck is matter? First off, chemistry is studying matter. Chemistry is studying substances. So it's important that we actually understand what matter is. And matter is defined as any substance that takes up space and has mass. Mass is specifically referring to the amount of matter a substance has, and volume is defined as the amount of space a substance takes up. I think that we're probably fairly familiar and comfortable with the idea of mass and volume, but just as a refresher, mass units are going to be often in grams, sometimes kilograms. The kilogram specifically is the SI unit for mass, but in chemistry, we're going to be focusing more on just grams. And as far as volume goes, remember, volume is the amount of space something takes up. Volume is going to be have the units of milliliters often, or liters, which is the SI unit for that. So it's really nice and helpful to be able to understand how we can kind of deviate and classify different types of matter. Matter can start by branching into two subjects or two fields. We have pure substances, which contain only one type of chemical within the substance, or a mixture. And a mixture is going to contain multiple types of substances within the substance, not chemically combined. Pure substances can then be split again into elements or compounds, and mixtures ultimately can be separated into two types as well, solutions or suspensions. We also call those homogeneous or heterogeneous mixtures. So what we're going to do today is we're going to focus first on the left side, looking at the different types of pure substances that exist in the world, and how to classify them. And then we're going to shift over to the right-hand side of this flow chart here and look at the different types of mixtures. So once again, a pure substance is defined as matter that has specific properties in composition regardless of the sample. And once again, we can subdivide that into the different types of elements or compounds that exist. For example, if I were to have a cup of pure water, and I were to cut that cup of water in half or pour like half of it out, the properties of the full cup of water is exactly the same as the properties as the half cup of water. Water has the formula H2O. By pouring some of it out, it doesn't change the composition or makeup of H2O. Water is water is water. H2O is H2O is H2O. A pure substance, in order to separate, for example, the hydrogen and oxygen that make up water, you would have to undergo a chemical reaction. And that's really the only way you can separate substances that are pure. So elements that are in a pure substance, or chemicals that are in a pure substance. So let's go ahead and look at the most basic type of pure substance, and that's going to be an element. An element is defined as any pure substance that's made of one type of atom. Atoms are, of course, the most basic form or type of matter, and we'll get into atomic theory in a little bit here, but really just for right now, you can think of atoms as tiny spheres that make up stuff. Some examples of this would be the sodium atom. Sodium in its elemental form is just Na. We can also have something like oxygen gas. Oxygen gas is absolutely defined as an element because it's a substance made of one type of atom. Now, O2 is a molecule. It contains an oxygen atom bonded to another oxygen atom. But in terms of its definition or chemical makeup, because it's made of one type of atom, the oxygen atom, it's just going to be an element. And another example of this would be white phosphorus, one of the allotropes of phosphorus. White phosphorus is 4 phosphorus atoms chemically bonded to itself. Here is a lovely picture of sodium metal. Sodium is a fantastic element to study and look at. It's extremely soft. You can cut it with a butter knife. And as I'm sure a lot of you know from prior chemistry classes or just your chemistry knowledge, sodium is so reactive that if you were to put it into water, it explodes. And once again, we'll look at why that is a little bit down the road. Now, I used the word allotrope earlier. When we're looking at elements, it's important to know that elements can combine in a variety of ways. Some elements can combine in a variety of ways. So an allotrope is just going to be different forms of the same element. One of the best examples of this is going to be oxygen gas versus ozone. Oxygen gas has the chemical formula O2. It's two oxygen atoms chemically combined. Ozone is O3, and it's three oxygen atoms combined. Now, they contain the same atom. They contain the same oxygen atom, but they contain different amounts, and that makes them chemically different. Ozone, as we know, is really good at absorbing ultraviolet radiation, hence why we have protection from the ultraviolet radiation which comes from the sun. Oxygen gas, not so much. Moving on to the more complex style of a pure substance, and that's going to be a compound. Now, a compound is defined really in just this very simple way. It's going to be any substance that's made of two or more different atoms. There needs to be different atoms within the substance. So, for example, a compound example could be sodium chloride, which would be NaCl. So it contains an atom of sodium and an atom of chlorine. Could be water. Water is a compound composed of hydrogen and oxygen. For every two hydrogens in the molecule, there's one oxygen. And one of my favorites is nitrogen triiodide, which is Ni3. It's this contact explosive, which literally means that if you were to touch it, it goes off, and it produces this wonderful purple haze over the experimentation. And you can set this off. You can set this experiment off with literally a feather. It's a really cool compound. But once again, all of these examples here are compounds because they contain two or more different atoms chemically combined. So moving on, we're going to go ahead and switch to the right-hand side of the flowchart. We're going to be looking at mixtures now. And mixtures are going to be substances mixtures retain their physical and chemical properties within the combination. Essentially, what I'm trying to say about this is that if you were to have example salt water, the salt contains and retains its physical and chemical properties, as does the water. And I think the more important takeaway from this is that the composition of a substance that's a mixture can vary. You can have salt water that's extremely salty, or salt water that has a few particles of salt dissolved into it, like our tap water. Tap water is technically a form of salt water. It's a solution. Or the ocean water, which is a very high concentration of salt dissolved into water. The substances within a mixture are not chemically combined, so it's fairly easy to separate substances within a mixture. One of the great examples of a mixture is air. Air that's around us right now is a mixture of 78% nitrogen gas, 21% oxygen gas, and 1% others. That's going to be like carbon dioxide, some water vapor, and even a little bit of argon, the noble gas. So when we're looking at this, remember we can look at two types of mixtures. We either have solutions or suspensions. Remember, a solution is also defined as a homogeneous mixture. And essentially in a solution, these substances and components are uniformly distributed throughout. Some examples of solutions are going to be substances that are dissolved into water, like salt water or sugar water. And alloys can be loosely defined as a solution or a mixture as well. When we look at a particle representation, essentially you're going to have alternating particles or an even distribution between the solute and the solvent, which we'll define a little bit more detail later. And it's not unevenly distributed at all. You can see that there's a regular repeating pattern of red particles and black particles here. Suspensions are defined as heterogeneous mixtures, and basically they're opposite of solutions. They're going to be when the substances combine, but not in a uniform distribution. Some examples of this would be chicken noodle soup. That's one of my favorite examples to use. But a more chemistry related one would be like oil and water. When we mix oil and water together, they spontaneously separate and form two layers. So oftentimes when we look at suspensions, you will either have like globular portions that are not evenly distributed throughout the water, or once again, you'll have very distinct layers that form, and the substances don't truly mix evenly. So with that being said, we are going to finish by looking at a few examples here. These examples are excellent for helping us identify if we're looking at an element, a compound, a solution, or suspension. And the best place to start with this is going to be this first one here, molybdenum. Whenever you're trying to identify if something is an element, compound, solution, or suspension, you should first look at the periodic table. Molybdenum is one of the elements on the periodic table, meaning that we can define it as an element. Moving on, if I were to go down the street here to the ocean and get a cup full of water from that ocean, there's going to be a lot of stuff. There's going to be like seaweed, maybe a fish if I'm lucky, some pebbles. So this is not an even, we know that it's a mixture, but it's not an even mixture. So it's definitely going to be a suspension. One of the best ways to identify that you have a compound is by writing the writing the substance's chemical formula after the name. Notice here that dextrose has a formula of C6H12O6. It's one of the isomers of glucose, but it contains different elements chemically combined, and they are all different chemicals, different atoms, so this is going to be a compound. Sulfur. Sulfur, at the end of the day, is 8 sulfur atoms chemically bonded to each other, but because they are all the same atom, we define this as an element. And then last but not least, ethanol. Ethanol is store-bought ethanol is sometimes as high as 95%. And that percentage basically tells us that the chemical ethanol, which is C2H5OH, is mixed with water, H2O. So this solution here, evenly mixes C2H5OH, ethanol, and good old-fashioned water. All right, so with that being said, don't forget you have the graphic organizer that follows along with these slides fairly well. And if you have any questions, feel free to email me.